Adjoint variables have to have some jumps. We already justified that by that example in the beginning. Then we did what's called the direct maximum principle. Now, the literature has both of them, direct and indirect, but I had decided a long time ago that I was following the indirect method. So the entire book, we apply, in solving problems, we apply indirect method. Okay. The indirect method, by that we mean that instead of adjoining the constraint directly, the constraint which is the state constraint h x u t bigger than or equal to 0, what we try to do is we try to adjoin the first derivative. The idea being that when the constraint is violated, or when we are on the constraint boundary, we cannot really control the constraint itself. We can only control the constraint by its derivative. So what we're trying to say is that when hxut is at the boundary, we would like this first derivative of h1 to be bigger than or equal to 0, so that it get pushed back into the interior or stay on the boundary, but does not go to the other side. That's why, as you can see here in 4.28, we applied a multiplier eta to h sub 1 or h super 1. Now, clearly, we also talked about that in case the first derivative of h does not involve u, and it's possible. We had the example in the train problem, for example. X dot was y, and y was not a control variable. So in that case, you have to actually go as far as you can until some control appears. Because only y are control, because we can only manipulate control. We cannot manipulate x. We cannot manipulate the state. So we have to go as far as that derivative where u appears. And those are called higher order constraints, and there are maximum principles available for that, but they are so rare, and most of the time the derivatives usually have a control, so we'll only look at the first order constraint. If you happen to have a problem where that is not the case, then you just go back to the literature. Okay, I do direct maximum principle because a lot of books do direct maximum principle. Some of the favorite books that I have, Saarstad and Soothsayer, that one of my favorite books, the people I know quite well in Norway, they use direct maximum principle. So I do put direct maximum principle because it is used often in the literature. So it is covered in this book. It was not covered in my first edition of the book, but now I'm covering it. Okay, so since the indirect is the one we are using in the book, we'll just try to review it very quickly, although we did it last time. So if there are any questions regarding the indirect maximum principle, please feel free to ask. So the indirect maximum principle, we adjoin the Lagrangian is right here, and that's where the eta is. Remember, in the box, we don't see an eta, but it appears only when we do the Lagrangian, because Lagrangian has an eta in it, and you see eta has a complementary slackness condition with h. Okay? We don't have a, by the way, we don't need the complementary slackness condition with h1. H is sufficient. Okay. So more or less the principle goes along the same way. We have a transversality condition, which is very similar, but now we have a gamma that goes with h sub x, and we have a Hamiltonian maximization problem at each point in time subject to the constraints. The constraints now you can see is two of them. One is g, which is already a mixed constraint. The other one is h sub 1. H sub 1 is now a mixed constraint. Okay, and remember, those are depending on which of the component of h is at the boundary. We impose only those components. Okay. Now, actually, that's also true with that. I mean, even if the G has many components as well, and only those components that are on the boundary are the one that is going to apply, the rest are not going to apply anyway. So I am not sure why I have to put H sub I, because if I just put H, it should still be okay. Because in the end, whatever is on the line is that's going to affect this. Okay. So then we have a Hamiltonian, and notice now there's a boundary, there's a jump condition on lambda, but it's also, yes.
Excuse me, I have a question.
Right.
So on the line 6, lambda t, capital T minus equal to blah 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 until gamma multiplied by hx.
Yes.
Then are we gonna use all of the, because we have hi, so which h should we use here? Although in the problems there's only one h usually, but what if there are two?
No. When you have vector constraints, right, there'll be two. The gamma will be gamma 1 and gamma 2.
Oh, okay, I got it.
Yeah, the gamma is going to be a vector. As you can go back to look at it, somewhere we must have said that because they have to be row vectors, which are going to be, that's an interesting thing. You raised this question, and it is basically all of those are going to be vectors. So so the Lagrange multipliers are always going to be for each constraint, right? So let me see if I have said anything anywhere. That is a good question. I mean, it should be said somewhere in chapter 3. I will look, but usually we should say alpha, gamma, beta are appropriate dimensions. Okay, so we should say that. I do not know if we did that on chapter 3, but let's not waste time on that right now. They are implicitly mentioned, but it would be a good idea to mention them anyway.
Oh, thank you.
Oh, hi, Professor.
We are all of those vectors are going to be, all of those are going to be vectors when there is a vector, because there's a one variable for each constraint. Okay, there's a one shadow price for each constraint. Yeah. Okay. Thank you for asking that question. I'll look into it. Well, let me look quickly. Somewhere we should mention that. Yeah, actually, if you go to yeah, we do mention, for example, for example, if you look at section 3.1, we do say A and a B, which are applied to the constraint, the terminal constraint A and a B. We actually say we see the A in a A and a B in particular space. Yeah, we do that. We say lambda in E sub n. If you look at the equation 3.8, so we do all of that. Mu, we also do that. So the only question is we did not do that for eta, maybe, but even that may be true. Just 1 second. I mean, each time we should mention that. You're right. Okay. We got lazy in section 4.3. We decided not to do the dimension on alpha, beta, gamma, and all of that. But in chapter 3, we have done that. And so I think it's a good idea to do that also in chapter 4. Is that clear now? If you go to chapter 3, we have dimensions for the shadow prices and adjoint variables. But somehow in chapter 4, they did not get in.
Okay, thank you. That's clear. Thank you, Professor.
But it should be understood. It's not a mistake. It's not a typo. It is probably better to put it there. Yeah. Okay. Thanks. So let's go back to yeah. So once we finish this, remember now there's a Hamiltonian condition, and if H does not have any direct component of T in the sense that the state constraint is independent of explicitly independent of time T. So it is the same for every time T, doesn't depend on seasons or whatever, then it turns out that the Hamiltonian should be continuous. Okay. Otherwise,
Excuse me,
that particular
Professor.
H.
Excuse me. I have a question regarding the notation.
Yeah,
So, here you use h sub t to denote the derivative with respect to t, right?
right.
Yeah, but in the previous indirect method, you also use h super 1. So are they the same or is there any difference?
The super one is a full derivative.
Um,
H sub t is partial derivative with respect to t.
okay.
So we put h1. The reason we put h1 is because if you put down below, we could
Mm-hmm.
put h prime if you want, but we cannot put h sub t because it is a derivative with respect to with x and a u and a t. So if you look at the derivative, then when we go to derivative first time, where is the first time we put the derivative? Just 1 second. 4.8. You see here, it's
Yeah.
dht. It's not partial
Okay.
derivative with respect to t.
Okay.
So we need some notation. You could put h prime, whatever it is, but here we have defined it.
Sure.
Yeah. Now
Yeah.
we cannot put down below h1 because that would be the component of the
Yeah.
vector. So that's why we put it. You could put h prime or h1. I put h1 because it's r equal to 1 here. It's a
Mm-hmm.
first order constraint, right? Now,
Mm,
if
yeah.
I needed r equal to 2, then I would have to go all the way to 2.
Mm-hmm.
So yeah, it's one or the other. Doesn't really matter. It's just a notation. We used it. So, okay.
Okay.
Thanks.
Thank you. Thank you, Professor.
Yeah. Okay. So notice now these constraints are at t minus because the problem is connected from 0 all the way to t minus. The reason is at t minus there can be at t itself there can be a jump because the constraint may be active at t itself. And we all know that that one is by definition this. Because remember, lambda is the marginal value of the state. For the marginal value of the state at capital T can only be this because there is no more problem. The problem finishes at T. So the only thing that is remaining is the salvage value of x. And the salvage value derivative of x is exactly the marginal value of x at that capital T. So lambda dt is basically done. It's fixed. But remember, the 2-point boundary value, if this is constrained, we cannot use this because this is not connected with the rest of the problem. The rest of the problem is connected with t minus. Okay? So that's the 2-point boundary value problem has to begin here on the other side, on the back. Or if you begin here, you have to recognize there is a jump. Okay, that's I'm not, but essentially here we are just giving formulas for the direct maximum principle. There's a formula, and it's different from the previous one, but the meaning of all those is the same. We we they are all in principle solving the problem for any t, and then optimize over t. And that, as you knew, we tried to do that before. So all of that can be done with some effort. That one, and again, um, the conditions for. I would probably ignore that for the time being. They are there to cover the literature in some sense because you might find them, but we don't really get some of that in the book right now. So let me um, get to the example now. I think we tried to do that. We already talked about this example. We covered this, right? If you're not, please stop me. Now, the
Excuse
sufficiency
me.
conditions are always mentioned in terms of direct maximum principle.
Excuse me, Professor.
Yes.
Can I ask a question?
Yeah.
On the slide, page 9, you said, page 9, the slide. Yeah, here. Why if xt greater or equal than 0 to 0, then h1 is equal to f, and if it's bounded by m, then it's minus f. Could you explain that one more time?
Oh, yeah. Because xt bigger than or equal to 0 is a special case of h of xt bigger than or equal to 0, right?
Yes.
This is a general constraint, state constraint, right? Pure state constraint. One of the special case of this is xt bigger than or equal to 0, right?
Mm-hmm.
That's just a simple function of x, right? It's identity, right? So
Oh, okay.
if I take h, then I have to take, because remember, when I'm at the boundary of h, on the boundary of this constraint,
Mm-hmm.
if I'm bounded at this constraint, I want to make sure that its derivative is bigger than or equal to 0, right?
Yes.
So that's the only way I can keep this constraint satisfied when it is at 0. When it is 0, and if this guy becomes negative, then we are going on then we're going in the negative territory, right?
Yes.
Okay, so the special case of xt bigger than 0, the x dot, which is h sub h1, right? H1 of this is just one first derivative of that with respect to t, right?
Mm-hmm.
Because that's dx dt, so this will be dx dt, right?
Mm-hmm.
But dx dt is exactly f, because dx dt is x dot. X dot is
Oh,
f, right? That is our problem, right? We look at our
yes.
problem. We begin with x dot equal to f, right? Well, I don't know.
Yes.
It's not here, but whenever we define the problem, x dot equal
Yeah.
to f, right?
Yeah. Yeah.
Yeah, c x dot equal to f, right?
Mm-hmm.
Now look
Yeah.
at what happens when you do m. If you do m minus xt bigger than or equal to 0, that is also a special case of this function, right?
Yes.
But this condition now is xt x. So because this is minus, so I have to find out what is the constraint. If constraint is minus xt bigger than, so the constraint is this. Take the derivative of this now. What is h1? The h1 is m.
Minus
There's
f.
no derivative. It's minus x dot, right?
Oh, okay. I got it. I
And
got it.
minus x dot is minus f, right?
Yeah. 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 I got it. Thank you, Professor.
Did we go through this? Yes. Anyone?
I'm not sure, but could you go through
Okay,
that one
why
more?
don't we do that? Why don't we do that? So we are now applying the same, so we are applying now the maximum principle to this particular problem, which is a governing problem in this chapter, which is example 4.1. Let's go back to example 4.1 to see what's going on. Example 4.1 is this, okay? Here there's a parabola, and we want to start our initial product is here, so remember we are maximizing minus u, so we are minimizing the integral of u, integral, which means we want u to be as low as possible in some way. So this is a rather trivial problem when it comes to intuitive application. So clearly x0 is u equal to 0 is the best way to go here. And then because remember, I cannot go below 0. If I was allowed to go below 0, I might do that, right? So for example, suppose I had 0. Suppose I had -1 here, then chances are I would apply -1 here and go here and then go up. That may be the optimal solution. That would be an interesting exercise. I never thought of that, but maybe I will give those as exercises in future. Okay. So we have idea what, so there's 1, the constraint is encountered at point 1, and then at 2, we leave the constraint and go into the interior. Remember, this is the interior of the constraint. This is the exterior. That's outside the constraint, which is not feasible here. This is interior because I can be all over here. Right. So now we already the example here was to demonstrate that somehow or the other, if I were to find the value function of this problem, then the value function is not differentiable at point 1, and it has a jump, as we can see this. Okay, so we got that exercise right there. Okay. I also want to say that it will be instructive for you. I did not do the value function for x less than 0. There's no reason for you. Suppose I begin at -1. Well, if I begin at -1, I have to find the value function all over here. So I have to go here and then go there and find the value function. And the reason I didn't do further down is because at some point, I cannot have the initial value x here. Because if I put the initial value x here and I go like this, then that particular point is no longer feasible because the slope here is bigger than 3. And I'm only allowed to have 3 control. So if I was low enough here, suppose I was here even. If I was here, I actually cannot have a feasible solution. Because the only way I can do is go interior. But if I'm here, there's a possibility that I will use control 3 to go somewhere here, and then go like this. So I have to join this curve at the place where the slope is 3. If the slope is bigger than 3, then I cannot do it. Okay? So that's what I mean by this. Remember that this parabola is going like this, and at infinity, at -infinity, its slope is infinity. So at some point, its slope is less than 3. Okay. So I didn't go through because then I have to find out all the feasible spaces, and that requires some formula. It's not difficult to do, but it just takes more effort to explain that in a class, and it's not needed for the point that I'm making. The point I'm making is that this vxt is going to be discontinuous at this point, or the derivative is going to be discontinuous at this point. That's the point I'm making. And so I'm solving the problem for x bigger than or equal to 0. Okay. And when x is bigger than 0, we don't go on this side. Remember, vxt is a dynamic programming. So if I begin with x and go to the other side, I need those values also. But if I take x bigger than or equal to 0, I will never go below x equal to 0. And so I don't need the value functions below x equal to 0 for my dynamic programming equation. Okay. But if I need to solve for vxt in all feasible x. So it might be a good exercise for you to find out, which are the feasible x's and how I find the value function from those feasible x's. It will take more than 3 or 4 pages to explain that. So What I'm doing now is solving that problem with, this is the solution of the problem with direct maximum principle. And we were indirect method, and we are, oh, we actually don't, I think we did that. We solved that, but I can go again. So the direct method we apply to this problem, and all we're trying to do here is to show that all of these conditions are satisfied, because we already have the solution, right? The solution is already there when we began this chapter. So all we do is write all the conditions of direct maximum principle. These are all the conditions we write. And then we write these conditions. We basically show those conditions plus the conditions on the, this is the jump condition on lambda. This is the Hamiltonian condition. So I can write all of those. So basically I rewrite the box conditions for this particular problem. And then I basically show that they are satisfied. So for example, since gamma d is equal to 0 from 4.20 right here, because this on this side is not 0, so gamma d has to be equal to 0. So if gamma d is 0 from 4.20, then we have lambda d 3 minus equal to 0 from 4.19. So this is how we have to go one by one. So this one gamma d, so lambda d 3 minus 0. So if lambda d 3 minus 0, then, and of course lambda d 3 is equal to 0 because that is exactly the salvage value, that's 4.14, which is given by the salvage value condition, which is this one. Okay? So we go, it's kind of have to go through all of these places. So there is no jump at 3. So 4.23 is satisfied. And then we have interval 2 to 3. Interval 2 to 3. So if you look at interval 2 to 3, interval 2 to 3, the whole x is in interior, right? So go through the, just kind of keep the picture in mind. This is 2 to 3. 2 to 3, we are in interior. So the constraint is not active. The constraint is active only along 1 to 2. It's active. It means it's right on the boundary. So 2 to 3, the constraint is not active, so its multiplier has to be 0. So eta d is 0 because the constraint is not active. And if eta d is 0, then we go to 4.19 and we fix the eta d is 0, so lambda dot d is equal to 0. So we can see lambda dot d equal to 0. And then we solve that. Because lambda dot d is 0, then its solution is lambda d equal to 0. And if lambda d equal to 0, then we go to complementary slackness condition here to show that mu1 equal to 1 is bigger than equal to 0 and mu2 equal to 0. Because mu1 is the bound, mu1, okay, mu1 and mu2 are multiplier of u. And u is 0 here. And u is 0 means the first constraint which applies u, which is mu1 was for u bigger than equal to 0. So since u equal to 0, u is 0 is on the boundary. So here we are getting mu1 equal to 0, but the u is not 3. U is not on the boundary of 3, so its multiplier is 0. So that's basically what's going on here. So we're going from 3, then 3 from 2 to 3. Then once we are at 2, we go to 1 to 2. 1 to 2, the control is strictly between 0 and 3. Okay, so mu1 and mu2 are equal to 0. These are the multipliers for control constraint. Since it is 0 u star less than 3, so we have these guys equal to 0. And then we go back to 4.18. So these guys are 0. So and Lagrangian is 0, so lambda d equal to 1. See, this is what is going on. Lambda d equal to 1, and And now we need to find out what is lambda dot doing. And lambda d equal to 1, then it's a lot of conditions. So 4.9, lambda d equal to 1. Where are we doing here now? Let me see. Then I could, that's 4.9 and 4.9 gives eta d, which is eta d minus lambda dot d equal to 0. So eta is the, let's see now. Yeah. Okay. This is the direct. This is okay in the direct maximum principle. Now, what is going on here is that eta d equal to 0 and eta d equal to 0 means, let me see now, which is the condition here? 4.19. Eta d equal to 0. Lambda dot d equal to 0. How did we say lambda d is discontinuous at tau equal to 2? Tau equal to 2, we are here. Oh, because lambda d equal to 1, and here the lambda d was 0. So because lambda d is 1 here and a lambda d was 0 here, so then we know that at 2, lambda d is discontinuous. I think it would have been nice to write here that, so that from previous case lambda d was 0, here is d equal to 1, and therefore lambda d is discontinuous. Is that clear? And so it's discontinuous, then we can go here at 4.23 to find out what is the other side. See, what's going on is that if you go back to the picture, these problems are difficult, as you know. If you go back to the picture, we are sort of going from here to find out what the lambda d is. Because this jump, we need to find out where the jump is, because otherwise 2-point boundary value problem can be solved. But with the jump, we need to solve the point in pieces. So we go from here to here, go here to here. Then we found the jump here. Well, once we find a jump here, then there's a new 2-point boundary value problem that begins here. Because on this side, lambda d is different, and this side, lambda d is different. And the jump is 1. So that's sort of what's going on there. Sorry. Okay, so once we got the jump, 4.23, so we got the jump, and that gives us the zeta d. And once we have a zeta d, we can put the zeta d in here and show that the 4.24, which is the Hamiltonian conditions, also satisfied. We just plug everything in there. We know the values of these quantities. We plug them in there and show that this is, I mean, that's why I want you to read these things at home, because in the book, you cannot explain everything. You cannot say, I plug in here, plug in there, plug in there, and rewrite all of these. It is not, that's not how you write a book, okay? So these things are something, you sit with a pen and paper, and you do the calculation. You substitute all the values that we find out going through this, or we know the values through the picture, the figure. You plug all those in, and the only thing that was missing was zeta d, and now zeta d is known here. So you plug in there and you find out that this also satisfied. So that way we can show that all of these conditions are satisfied. And remember, these are necessary conditions. They must be satisfied. So we We conjectured a solution which was very reasonable, and we now show that the direct maximum principle is conditions are satisfied, and so that's that. Okay. You can see the difficulty of two-point boundary value problem because two-point boundary value problem doesn't know what the jump is. And without the jump, I cannot go from backward because we need to cross that jump place to continue going all the way to time 0. From time 3 to time 0, if it's not continuous, I need to figure out, where to make the jump and what the jump is. So when it comes to state constraint, you will see the literature does not usually use two-point boundary value problem for solving those problems. They go through what is called gradient techniques, which are more akin to nonlinear programming or math programming. Okay, but I am not an expert on computations at all. I gave up a long time ago, and so the only time I had a computational chapter in the book was in the first edition. After that, I abandoned it because I cannot keep up with it. So as you can see, lambda dt is 1 up to 2, and 2 to 3 it is 0, so there is this jump. Okay. Max sufficiency conditions are similar to what we did in 3, as long as, so we can say the jump parameter at each tau, lambda d is discontinuous, satisfy the necessary condition. So these all satisfy necessary condition. If the maximized Hamiltonian is concave, and in 4.11 S is concave, this is very similar to what we had before, and G is quasi-concave, again similar. H, now the H is new thing here, but H also needs to be quasi-concave. B is linear because it's a equality constraint. So equality constraint cannot be, it's both quasi-concave and quasi-convex, then it would have to be linear. Because equality constraint B linear can be expressed as two inequality constraints: B bigger than or equal to 0 and B less than or equal to 0. B bigger than or equal to 0 required it to be quasi-concave, and B less than or equal to 0 required it to be quasi-convex. And both of them means it has to be linear. Same thing we did for chapter 3. So if you're using the indirect maximum principle, which we're going to do in the most of the book, and if you are asked to do the sufficiency condition, you have to convert the indirect multiplier to the direct multipliers and then use this theorem. There is no direct theorem for indirect maximum principle. So that's one of the drawback of indirect maximum principle. On the other hand, it's easier to apply because it is more intuitive. So now we have a direct maximum principle, indirect maximum principle. We now have a Hamiltonian. The Lagrangian now is eta times h1. And so we can just go through very quickly. We have if the stars are all the values that are along the optimal path. And this is the transversality condition on lambda t minus, and Hamiltonian is maximized. We already talked about this. Boundary condition and the jump conditions on Hamiltonian and lambda, or we usually call it continuity conditions on Hamiltonian and jump condition on lambda. But as you can see, Hamiltonian, if H itself depends on time explicitly, the Hamiltonian can also be discontinuous. Now what we do? We have some conditions that we now obtain the multiplier direct maximum principle for those in the indirect maximum. these are these are these are available in the literature, and one of the best reference I can tell you is my survey paper, which is quite well known. It's a Hartle, Sethi, Vixen survey in Siam Review, where we actually derive these conditions. And knowing those conditions, what happens is we have, because eta d is bigger than or equal to 0, then the derivative of eta dot in the indirect maximum principle has to be less than or equal to 0. But we don't put that condition in this. We don't put any condition on eta that less than 0. But from the direct maximum principle and the relationship between the two principles, one can show that this eta dot should be less than or equal to 0, and one may put that into this condition, because more conditions there are, the better the necessary conditions. Because your necessary conditions are trying to reduce, because feasible controls are all, and necessary conditions will reduce the candidates for optimal control. Okay, so more reduction, the better. If you can get to uniqueness, then it is even sufficient. So what I'm trying to say is that these are the conditions that one could impose on these multipliers in the indirect maximum principle. Well, we don't do that. We don't do that. The literature doesn't do it. Some people even think that condition may be implicit in other conditions, but nobody has proved all of those things. So all I'm saying is that these are serving as remark because you might encounter them in the literature. We don't use them in this book. I use them in the 3rd edition, but the 4th edition I even removed those things, because some of my colleagues from Norway, who are quite experts, also said that it's not a good idea and just leave them as a remark. If you go to 3rd edition, I had put eta dot less than 0 in this box. That's been removed. So those are okay. So this is going one way. This is tell you how to go from indirect to direct. So if I had indirect maximum principle, I can find the direct multipliers. That one says how to go from direct to indirect. So these are all available in the literature. I say it to them. And this is the reverse of the other one. One requires differentiation, another requires integration. But they are what they are. And there's not much to be said. I don't think there's much in the literature to be said. All we knew about these is in my survey paper, and one can go there. But I know more. I don't know more than that. Okay, so you see these sitting as a remark. We don't put them in the condition. We don't put them in the box. We just leave them as a remark. Use it if you have to use it. In your research, if you can use it, it'll be a great thing that you can show that you used it. But otherwise, so if I have that, it means that I can, given that I knew that the direct multipliers from our solution of the example, I can actually do the indirect multipliers as well. So one way you can do is to resolve that 4.1 using the indirect maximum principle, find the indirect multiplier, and verify that these conditions are satisfied, because you will know both set of multipliers and you can find out that these conditions are satisfied. So it's one way gives you an intuition of that these conditions make sense. These transformations make sense. So I chose to not solve the 4.1 problem with the indirect maximum principle, because you can just get those multiplied directly. And so I solved 2 different problems. So the first problem I solve is this one. Here we have x bigger than or equal to 0 as a pure state constraint. And this is similar to example 2.3, except that I impose this constraint. Okay. So let's now apply the indirect maximum principle. Hamiltonian is minus x plus lambda u. And a u star of x lambda, which is now special as a function. Notice this is an abuse of notation. Mathematics people would say that that is not, because we use u star t as an optimal control. I'm using that as a feedback form. Some people would say that you should use maybe u star hat or something because it's not the same function. But that's just too much notation. And I think most people who would look at it would automatically figure out what we mean. So I don't change the notation. U star x lambda then is bang minus 1 lambda. It's very important for you to understand that in most mathematical papers, you need to economize, and people do economize on notation, because otherwise it becomes very messy. And when you economize on notation, you need to have some sense of what these things mean. Because if you don't have a sense of what these mean, then you are kind of out to lunch. For example, if I give you h minus x lambda u, clearly I don't see any t in there, right? And if you take the derivative of h with respect to t, you just say it is 0 because there's no t on this side. And I actually had people who did that, and then you can sort of see that they are basically have no clue of what's going on. Okay. So when x is equal to 0, we need to impose this constraint. X dot, which is u, has to be bigger than equal to 0. Because we need to impose this constraint, when x is 0, I cannot use minus 1 because u has to be bigger than equal to 0. So what I'm trying to say now is that this bang function has to be defined differently for x bigger than 0 and x equal to 0. So u star x lambda is bang minus 1 lambda, but u star x lambda for x equal to 0 is bang 0, 1 lambda, because I cannot go to minus 1. I must, the lowest control that I can use has to be 0. And the highest control I can use is still 1. I could have put 0 here and not say this. That's another way to do that, but that's what it is. I have a bang function that needs to be re-specified for the boundary. Okay. So that's the first difference between example 2.3. That's a difference. That's the main difference now, because the controlled form has to change. Lagrangian, as we have in the indirect maximum principle, eta times u. Then we have conditions which are complementary slackness condition, and we have a condition on Lagrangian. This, by the way, is very similar to Lagrange multiplier in calculus. So it basically says that while the objective function derivative cannot be 0, but the derivative of the Lagrangian must be equal to 0. So the Lagrangian condition gives us 1. And remember, we need to have lambda 2 minus, which according to our box would be gamma, and gamma is bigger than or equal to 0. That's a complementary slackness condition on the control, on the state. So we have this. Now we have to guess a control, and the control we guess will be one that keeps x star as small as possible. So you go back to example 2.3, that's what we did. So u star equal to minus 1, t from 0 to 1, At that point, remember x began at 1. So at that point, that x will become 0. So the x will become 0 at that point, and we switch the control to 0. So there's a picture here somewhere. We go from here to there with -1 control, then we switch to 0 control and go all the way up to here. So that's our trajectory, optimal trajectory. All we now want to find out is what the lambda is. Okay. But lambda, we need to find out what is this value gamma, right? And gamma can have two values. One can be 0, and one can be x2 is 0. So right now we have, as you can see, x2 is 0. x2 minus is 0. This is x2 minus 0, in which case we can have gamma bigger than equal to 0 or gamma equal to 0. We can have either, right? So we start with, to obtain lambda t, let's first try lambda 2 minus, which is gamma equal to 0. Now x star t enters the boundary at t equal to 1. If enters the boundary at t equal to 1 at this picture, the jump can only happen here, except it can here, but we are beginning at 2 minus. So whatever jump happened at 2 minus is taken care of. So from 2 minus all the way to 1 plus, there cannot be any jump. So we can actually integrate the lambda dot equation to find lambda all the way up to 1 plus. That's what we're going to do. So then there are no jumps in the interval 1 to 2. Well, actually we included 2 here because we already decided that lambda 2 doesn't jump, because lambda 2 we already know is 0 because there is no salvage value. So lambda 2 is 0, and lambda 2 minus we also now assume to be 0, so there is no jump all the way to 2. If I put this to be bigger than 0, then I would have to go open interval here. So we solve, and we get lambda t equal to t minus 2 from 1 to 2. So we basically get this equation. No, we get this equation. Up to 1 open. Okay. Now we have to go this side. For this side, I cannot continue like this because it will go like this. I need to find out if there's a jump. Since lambda t is less than 0 and x star t equal to 0 from 1 to 2, we have u star t equal to 0 by 4.40. So we know that u star t is equal to 0 all the way on this segment. Now let us see what must happen at t equal to 1. We know from 4.47, from this one, I can find out what is at 1 plus. So 1 plus, you put 1 here, you put 1 here, 1 plus is minus 1. So lambda at 1 plus is minus 1. Now, to obtain lambda 1 minus, that means we need a jump, we can go to Hamiltonian. So Hamiltonian, since h, this is h, state constraint. It is not explicitly dependent on time. If it's not explicitly dependent on time, then our box says that Hamiltonian must be continuous, because this quantity will be 0, and so Hamiltonian must be continuous. So let's use that condition here. H1 plus, yeah, the definition of Hamiltonian is x star 1 plus lambda 1 plus u star plus 1 plus. All of them are 0. This one is this one is 0. This one is minus 1. And this one is 0. So this whole thing is 0. What is h1 minus? Well, h1 minus, this is still 0 because at 1 and 1 minus x is continuous, so x is 0. Lambda 1 minus we do not know, but u star 1 minus we do. U star 1 minus is minus 1 right there. So we can put minus 1 there. And once you put minus 1 there, we say h1 minus is minus lambda 1 minus. They have to be continuous. So h1 plus and h1 minus has to be equal, which means lambda 1 minus is 0. So once lambda 1 minus is 0, we know the jump is equal to 1. Zeta 1 is the jump which is equal to 1. Look at the picture what happened. We started from here. We integrated lambda. We arrived here. We found what the value of lambda 1 was here. Plus, lambda 1 plus. Then we put the Hamiltonian condition, and that tells us that lambda 1 minus is actually 0. So that's your jump. The jump is exactly, so the lambda 1 actually jumped. If you go this way, lambda 1 jumped downward. But if you go this way, then it jumped upward, okay? But usually we say it downward because we go in forward direction. So lambda 1 jumped, and that's 1. So we start here. Now again, we can integrate lambda because we know lambda dot equation and we know the value here. So we can integrate that and we can find the rest of the lambda. So once we have this, we have lambda 1 minus equal to 0. We can integrate lambda t again. And when we integrate, we know lambda t is less than 0. If lambda t is less than equal to 0, and x star t is 1 minus t bigger than 0, we know the control is going to be minus 1 because lambda t is less than 0, and bang bang principle tells you that I can use the first bang. The first bang tells me minus 1. And so the x is strictly bigger than 0. We can find all the mu's, and mu's, those are very simple at this point. And so we have the whole solution. That part is very simple. The only thing I want to point out is that if gamma is, our guess is correct now because all the conditions are satisfied. So we do not need to go gamma 1 bigger than 0. You might want to try that at home to see, and then you will find that one of the conditions will not be satisfied. At least one of the conditions will be violated. And then you have to go to this guess. So if you start with this one of them will be violated, then you have to go back to here. So our optimal solution then is to go from here to here with control minus 1 and control 0. And lambda goes from here and then back to here and back to here. Notice now, here we apply the bang. We apply this because x is strictly bigger than 0. And this tells me control is minus 1. That one, so let me see what's going on here. So here we apply the first bang. Here, lambda is still less than 0. But now x is equal to 0, so we apply the second bang. The second bang says u star has to be equal to 0. So the second bang is satisfied here. First bang is satisfied here. Okay. Now, notice, even if you went all the way down here, we will still have the same solution. But lambda will not be satisfying the maximum principle because it will not be the marginal value. It will not be the derivative of the value function with respect to x. And so it will not satisfy the necessary conditions. I will not say anything about this remark, okay? These are very esoteric remarks. And here, to satisfy the sufficiency condition, notice I have the lambda and eta, and I can then, from lambda and eta, I can use this condition, to find, no, I can use this condition to find lambda d and eta d, etc. Okay, so that's what I'm going to do. And then I can, once I find this, I can use the sufficiency condition of the maximum principle. That's what I'm doing here. So lambda d, using that condition, is like this, t minus 1 and 0. And the Hamiltonian now is given by this with respect to lambda d. And this is concave because it's linear, so it has to be concave. So maximize, so this is concave, and these functions are linear and therefore quasi-concave. S is 0. And so all the conditions of the theorem, sufficiency theorems, are satisfied, trivially satisfied. And so we know that example 4.3, optimal control satisfies the sufficiency condition. Example 4.3, I go to t equal to 3, and I also put another condition on x3 equal to 1. Now the solution is obvious. If I go all the way to 3 here, it's so obvious that I don't even put a picture here. I think there is a picture in chapter 3 of a problem of this kind. So it's clear now that in order to go to 1 in one time interval, I would have to use +1 control all the way up to here. And the control, as you can see, is between 0 and 1. Control is between -1 and +1. So I use the +1 control all the way to get to x3 equal to 1. So all we're trying to do now is we know all we're trying to do is to this is our control, and all we're trying to do is compute the adjoint functions for this control. Notice now that there is a jump at lambda 3. To apply it to maximum principle, you will see that there is a jump exactly at 3. Now we go back to example 4.1, but rather than repeat that example, which we already solved for direct maximum principle, and we would have the indirect maximum principle multipliers anyway. So we decide to change the problem a little bit and put a discount rate. Right here. It's a finite horizon problem, so I don't really need to use the current value formulation. So I'm going to use the standard formulation. So I use now the indirect maximum principle conditions, which using the box, we need to put all of those conditions one by one. And we need to put some conditions at the entry time, which are the jump condition on lambda and the Hamiltonian. And by the way, the control, if the discount rate is bigger than 0, that's not going to change the control. So the control will remain identically the same as before, and we can basically solve the problem and obtain various multipliers. I just want to show you that this is basically we have the solution and just go one by one, just like we did in the direct maximum principle, and find all of this. I also want to show you, to tell you that if you put rho equal to 0, then we will have the multipliers, indirect multipliers for this problem. And once we have the indirect multiplier for this problem, it would be instructive for you to have all the indirect multipliers. We already have the direct multipliers. So you can go back to this and use these conditions and these conditions to show, to see that the two multiplier sets are related. Okay, so that would be a little bit of a something that will give you some sense of what is going on with these two sets of conditions. By the way, somewhere either in the book or another time, I have also put this condition, this problem when rho is not bigger than 0, but rho is less than 0. It's the opposite of discounting. And if it's less than 0, it means, so what does rho bigger than 0 means? Rho bigger than 0 means that the values that are further in the future are not so important. So if you look at rho bigger than 0, and you go back to this problem, we cannot do much here. What we want to do is we want to show if we can do anything here so that I can avoid some possibilities, because there's a cost can be traded off between this point and points further. So if rho is bigger than 0, initial values are more important than the final values. And you can see initial value, I have done the best. But if rho is less than 0, then if I can reduce the control here and increase the control here, which means I can have a higher cost here and trade that with a lower cost later, then there's a possibility that for rho less than 0, you might have a different solution. Okay? That's something you might want to think about and see how you want to do it. For example, at some value of rho, remember now, this is an expensive control. This is not 0. This is the cheap control. I mean, this is the best control for us. This is the best control for us because of the objective function, right? I want u to be 0 as much as possible, right? But I don't want u to be bigger than 0, which is going on along the boundary. So one can think of the following. Suppose rho is less than 0. If rho is less than 0, then it is better for me to change some of these guys to 0. Right? If I change some of these guys to 0, which means that this particular branch that I have here can be extended all the way up to here, let's say. So that means along this interval of time, 1 to 2, my control will be 0 rather than along the boundary. But if I want to do that, then somehow I have to get there. If I have to get there, I need to increase the control here. So for example, I can use the control 1 all the way up to here. Then I have a higher cost. I have a higher cost here because I'm not using 0, I'm using 1. But then from then on, I have a lower cost compared to this one. So you can see that for rho less than 0, or at least for some rho less than 0, it is possible that this optimal control will go from here to here and then straight there. I believe I have given that example one time before as an exercise or something. It may even be there in the book. But just to tell you that rho less than 0 and rho bigger than 0 may have very different consequences as far as this problem is concerned. So this problem is a rather nice laboratory problem that allows you to do lots of things. This problem was invented by me and Hartle in our survey many, many years ago to bring out the ideas of the state constraint. Where are we? We are here. This is straightforward. Current value maximum principle for the state constraints. We also, if you want to apply current value, we need to have a Hamiltonian and maximum principle for that. This is something we did before. It is, I don't want to do it again. Basically, the lambda dot, one lambda is related by other lambda by e to the rho t term, because this is the current value lambda, and the present value lambda and current value lambda is e to the rho t times the present value lambda. And so you can just transform the whole setting to the new setting, and the new setting gives you a maximum principle. I just want to point out some differences so that you know that it is not the same. One difference will be, if you look at it, one difference is going to be here. You see rho lambda f? This is not there in the previous case. So this is one place where you have a difference. There may be another difference somewhere. Let's see. Oh, so that's one difference in the box. Okay, so just make sure that that is a difference. The other difference will be here. You will see that this formula is not the same. There is some term coming in that is not the same. But there a straight transformation from one to the next, and you is this left as an exercise? You see, I'm thinking of more exercises as I go along. Here the remark also changes. Eta dot was less than or equal to 0. Now eta dot will be less than rho times eta t. This is the survey, by the way, I'm talking to you about. This survey was quite a lot of work, but it is quite well cited, and it is one of the top journals in the control theory field. So it was quite useful to do that. These are the Norwegian guys that I told you about that are that had a very well-known book in control theory, and they are mathematicians. And I visited them one time in Norway. Okay, any question regarding chapter 4? Okay, we're going to go to chapter 5. So the good thing is that the theory part of the optimal control is more or less finished. We will have a little bit more theory when we go to discrete time in chapter 8. But accepting that, the rest of the book is all applications. The applications of the theory to problems in production, finance, marketing, economics, etc. And the optimal control theory was still new when I was doing my PhD, not new in economics, but management science, it was new. And so my thesis had lots of applications. The thesis ended up becoming 10 papers published. And Thompson and I decided that since I had applied to so many problems, why don't I write a book? And so we decided to write a book. And the book has, of course, other applications, but I would say that half of the book is based on my thesis, because the applications that we did in my thesis were rather interesting and were not complicated enough to be part of a book. And so that's what we did. We basically wrote the book together. Basically at the CMU campus, I used to go back and forth to work on the book with Thompson, and basically we sat across from each other and wrote the whole book. And every time we came up with something that we wanted to put as an exercise, we actually put the exercise and solved the exercise as we went along and started putting exercises. And at some point, we came up with a topic that we thought was not done. So we stopped writing the book and published a new paper. And it went on for a few years until the book was finished. But now, of course, it is quite different from the first edition of the book. A lot of new things have happened. And so now, fourth edition of the book is in your hands. Okay, let's go to chapter 5.
Professor, can I
Yes.
ask a question?
Yes.
So could you go back to slide 34?
Yes.
Actually, slide 32, sorry. Yes, so here on the first line, we have lambda dot equal to 1. And then we apply that lambda dot equal to 1 for the interval 1 to 2.
Yes.
And then on slide 34, we have lambda, oh, sorry, I saw it wrong, sorry. It's lambda t, not lambda dot t. So it won't change, right, throughout the intervals. Lambda dot equal to 1.
Well, lambda dot is coming from the Lagrangian derivative, right?
Yes, yes.
So lambda dot is coming from minus delta L delta x, which is equal to 1. That's going to just stick around as 1, because if there's no control, there's no nothing, it's not going to change, right?
Oh, yeah.
Look at the Hamilton, look at the Lagrangian. Lagrangian is this quantity, right? And this quantity has a Hamiltonian, so Hamiltonian is minus x plus lambda u, right?
Oh, sorry, I'm confusing.
So there's going to be minus x plus lambda u, right?
Yeah,
There's no x here. There's no x here.
yeah.
So the lambda dot is minus delta L delta x, which is going to be 1, because there's only minus x in the Lagrangian. So lambda dot will not change. Lambda dot can change if lambda dot had some other things. For example, if I had lambda here, well, let me see now. This is the derivative of x, so it's minus. If I had a constraint, see, eta is u now, right? Eta is because of the constraint. Eta is on x dot, right? But x dot may have x term in there. I mean, h1, for example, will have x term in there. So let's look at h. H in the indirect maximum principle is in the indirect maximum principle, h will be h1 xu, right? See this one? This one?
Yeah.
That one would appear here. That one appear here, right? Eta times h of xu. And then delta x will have eta in there, right? And eta is gonna eta in there and x in there, and they can change, right?
Yes.
Yeah. But even in chapter 3, lambda dot can be on the right hand side can be x, right?
Mm.
We had already problems in chapter 2 where lambda dot on this side is some x. And so it's a 2-point boundary value problem. You already solved that numerically, right?
Yes.
If there's x on this side, lambda dot is going to change as x changes, right?
Yes.
So they are both going to be simultaneously changing. And so we cannot solve one without the other.
Mm.
And that's why we have 2-point boundary value problem. So the examples that I give you sometimes are simpler than the general cases, and they might give you a feeling that everything is so easy and everything is fine, but it's not the case. Yeah, in general, the lambda dot can change with respect to, because right hand side doesn't have to be constant, right?
Mm.
It can be a function of x. It can even be a function of lambda, because we have lambda times f, right?
Mm.
Lambda times f, and f can be a function of x. In general, it is. So lambda dot on the right side can have a term in lambda, can term in x, and in state variable, state constraint can have a term in eta. So it can have lots of different things.
Mm. Okay. Thank you, Professor.
Can you see chapter 5? Or I have to reshare it?
Yes, we can see it.
We can see that.
So what I'm going to do is I'm going to spend a few minutes just to get to the problem, and then we will take a break and then start with the problem, okay? So let me first, the chapter 2 will contain 2 problems. One is called a simple cash balance problem, and one is called the optimal financing of a corporation. That will be done finite and infinite horizon. There'll be a numerical example, and that problem of financing will eventually also, we will be working on investment problem in chapter 12, which will be stochastic. So first of all, the entire chapter is not stochastic. So let me just mention that this finance chapter is now looking at the current state of the world. It is deterministic. The finance problems are no longer deterministic. At one time, economics was a deterministic field because people in economics did not know much about probability, and they also solved the problem basically in a deterministic setting. Only much later, the economics people started becoming stochastic. And now, of course, it's quite a bit. Finance, long time, finance remained deterministic. I remember people who wrote their thesis on deterministic finance. One of them would be in right here in this chapter that I mentioned. But these problems are here now to explain various aspects of the control theory. I do want to mention that the cash balance problem is kind of like inventory problem. You know, cash is more like an inventory here, and it is more like an inventory problem. In fact, the Nobel survey that I sent you, I only just before I sent that to you, like maybe a day or 2 days ago, I have introduced a little bit of a paragraph on cash management problem there, and it's done by Merton Miller and OPRE. Merton Miller was a guy who got the Nobel Prize for his theory called Miller-Modigliani theory. And I had known Miller and OPRE paper, 66 paper, when I was writing my simple cash balance problem. But I forgot that Miller was the same Miller who was a Nobel Prize winner of MM. That problem is totally deterministic. It basically uses the economic EOQ model that we all aware of. It uses a slight extension of EOQ model. And only I finally realized lately that that Miller is actually the Nobel guy Miller. Because, usually we don't sometimes put the full name. So Merton Miller could be M. Miller, M. Miller can be million people. And so I actually included that paragraph only just on February 20, well, just a day or two ago. And then now that paper has been loaded on SSRN. But you can see that that particular paper is deterministic. Cash management problem, deterministic, published in 1966 in one of the top journals in economics called Quarterly Journal of Economics. So at one time, that was the case. The second problem is a problem of financing of corporation. That was a thesis at UCLA by one of the person named Lee. And they published a paper which was basically wrong. And when I looked at that paper in another context, I realized that they made a big boo-boo in there. And so I rewrote the paper. And I was very kind to them. I rewrote the paper. I told them that it should go to some other than people at UCLA, because one of his professors was a UCLA professor. And the journal was a top journal in Journal of Financial Quantitative Analysis. It's now one of the top 5 finance journals. And so they rejected my paper, and I looked at the review, and in those days the reviews were came in not in by email, internet. They came by regular mail, and there was a paper on which the review was, and you could see the watermark, and the watermark said UCLA. Now I cannot say guarantee that it was the same guy, but I'm 100% sure that it would be the same guy. But I cannot write to the journal that it is the guy. But I did write to them saying that the people who reviewed this article do not know anything about control theory, and please send the paper to somebody who does. And the journal was nice enough to send it to somebody who knows control theory, and the paper was accepted. So I basically prevailed on that. So what you see is my extension or my correction of the paper that I will talk more about, Krauss and Lee paper. And I think it's a very, very nice paper to bring the idea of what is called the reverse time technique, because we can solve this problem explicitly, and it gives you lots of a nice technical analysis of control theory that would be very useful. So I keep that, but both papers that you cover in chapter 5 are papers that are mine in some way. And I only want to say that the journal did accept the paper and said something about, do cite the previous thing, whatever. But I basically said that no, I'm not going to do it. And I given that they rejected the paper because it criticized their own wrong paper, I became slightly mean, and I changed the title of the paper called it used to be called Optimal Extension of Krauss and Lee. I changed the title to Optimal Correction and Extension of Krauss and Lee. So I put the word correction in the title. So I'm sorry, but I did that. I was a young man at that time and had probably not so many, had a lot of rough edges, I suppose. Okay, so So before we take the break, um, we will then come to here to start working on the cash balance problem. Okay, so let me take a break right now, and we'll be back in 10 minutes. Is everyone here?
Yeah,
Yes, Professor.
Okay. So we begin with a cash balance problem. And basically, the firm has a demand for cash, and it wants to meet those demands at a minimum cost. Basically, when the firm sells the products, it receives cash. And when it uses machinery and whatever the labor, wages, whatever it needs to pay. And so the net cash flow can be over time, can be positive, could be negative. And so when the cash comes to the company, it needs to put the cash somewhere. And it has basically two possibilities. If it keeps too much cash, which doesn't earn anything, then it loses money in terms of the opportunity cost, because by investing this cash somewhere else, you can earn higher rate. And if it's too small, then the firm has to sell these investments to bring the cash, and there's a broker's commission, and there's a cost. So the problem then is to find the trade-off between the cash and security balances. So let's assume T to be the time horizon. XT is the cash balance in dollars at time T. YT is the security, which could be a bond, could be a savings account, which earns some interest. We are not looking at stocks, which has a lot of uncertainties. And if you start investing in stock, then we're going to go back, then we're going to go to chapter 12. Okay, right now, we don't do that. Oh, just a minute. 1 second. Yeah. DT is the instantaneous rate of demand for cash. It is basically the cash flow, okay? It could be positive or negative, and I mentioned to you, I call it a demand, but Miller and Orr call it a net cash flow. That in the 1966 paper, which now you have a paragraph of that paper in the paper that I sent you. UT is the rate of sell securities in dollars, and negative sales means a purchase. R1T is the interest rate earned on cash balance. So I'm actually giving a little bit of interest. It could be zero. In Miller and Orr case, it is zero. And R2T is the interest rate earned on the security balance. In the Miller and Orr case, it's a bond or a savings account. Alpha is the broker's commission, and this is proportional. So this is where this paper departs from the Miller-Orr paper. By the way, I'm giving you Miller-Orr example now only because it's fresh in mind right now, and I forgot about it for many years. Miller-Orr basically has a fixed cost of transaction. So if you want to sell the bond, you have to pay fixed cost. And fixed cost means EOQ type model, because fixed cost means you cannot trade continuously. You have to trade only at certain instance when your cash balance is out of whack. So on one hand, this model is more general. It allows you a dynamic, continuous kind of problem. On the other hand, it does not allow you fixed cost of transaction, which makes the problem complicated in other ways. So with that, I will describe the model.
Excuse me, Professor.
Yes.
Why is the interest rate for cash balance and security balance different?
Security balance would be amount invested in bond, let's say.
Oh, okay.
And cash balance could be, let's say, checking account.
Okay, I got it. Thank you.
Okay. So how does our state, which is the balance in dollars, change? Well, it increases because I'm earning interest. Okay. Remember, this R1 can be a function of time. Remember, I had this R1 here. In general, it can be a function of time. This D is the demand for cash flow, so it's minus. But remember, the demand can be also receipts, account receivable versus an account payable kind of thing. And U is the trade that I'm going to make. And U, remember, is the sale of securities. So when I sell securities, I get more cash. But when I sell securities, I pay commission to the broker. But if I buy the securities, U is negative, and so my cash balance goes down. But whether I buy or sell, the broker takes the commission regardless. And so the commission is based on the absolute value of U. Okay, so remember, the absolute value of U is not allowed in our formulation because we are assuming that the function f, x dot equal to f, was continuously differentiable in all its argument, but U is not continuously differential at U equal to 0. But we'll see what we can do about that. In fact, we already told you what to do about it in chapter 3 when we broke this into U1 and U2. But now we will see a little bit more of it, a use of it actually. Initial balance is 0, x0. Y dot is our bond balance or security balance. It earns a bigger interest R2Y. And of course, this is plus U, so this has to be minus U, and I have initial value Y0. So I have now two state equations. But it's only two, so I don't use a vector notation and then put x1, x2 and make it more complicated. I just use x and y, and we let it go with that. I restrict the u to be between these two bounds. They are given to be constants. The objective function, there are two ways to write it. One is that you can you can accumulate all the interest and securities as you go along over time and integrate it. But you know, that's going to be the same if I maximize my wealth at time t, capital T. My capital wealth at capital T is the sum of the cash balance and the security balance. Then if I did very good all the way across, then that maximization is same as, you know, counting the cash earnings at each point in time and integrating it. Remember, I'm assuming a short horizon, so I'm not using a discount rate. You could if you want to, but I'm not using it. So you can see that the Meyer form can be intuitively argued to be the same as the Bolza form, where I would have to integrate all the earnings that I have at each point in time and then give you the net, maximize the net earnings. Okay. Well, the net earnings would be the same if I take the xt plus yt and subtract from this x0 and y0, then that's my earnings, integrated earnings. There's no discounting. So xt plus yt minus x0 minus y0 would be exactly the integral of all the earnings. And so you can see the Bolza form and Meyer form are not just mathematical nicety. They are also have a meaning, very practical meaning that we can see. And because of their meaning, I don't even want to convert one to the other. I write the problem exactly into Meyer form to begin with.
Excuse me, Professor.
Yeah.
I missed it when you were explaining the absolute value of U in the X dot. So does that mean that the broker's commission will only give that to the purchase?
No,
Uh,
so the broker's commission always goes to the broker, right? So it is negative, but let's say broker's commission is 1%, okay? So the
mhm,
alpha is 0.01, okay?
mhm.
And if I sell $1,000 of securities, I will pay $10 broker commission, right?
Oh
If
yeah,
I
yeah.
buy the $1,000 of security, I also pay $10.
Yeah,
I
yeah.
use a symmetric. I mean, you can use non-symmetric. It's not a big problem. I can do that too.
Okay, I got
But
it.
it's just
Yeah.
to make it simple. So lambda 1 dot is the derivative of the Hamiltonian, that's x, and lambda 2 dot is the derivative, that's y. You can see now I have two variables, right? Just like in the train example, we had two. Now we have two variables because we have two state equations. And this is Meyer form. And so this is only the salvage value. And its derivative is 1. So we get 1 in each. Because this is all lambda, there's no x, no nothing. And R1 can be a function of time. So I can easily integrate those equations. This is, by the way, the same as interest earned from T to T on $1, so that's that. And lambda 2T is also T to T with the security. So the meaning is very clear here. So the lambda 1T is the future value, means at time T, or $1 held in cash account from time T to T. So if I had $1 at small t, and I just kept it, that $1 all the way to capital T, then that's the amount of interest that 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 I would get. It's continuous. Continuous interest means it's e to the time, okay? Same for lambda 2. If I had $1 security from T to T, and they are earning me R2T at small time t, then we get this interest. Notice, if this was a constant, then it will be e to the R1 times capital T minus small t, which is what you would expect, right? E to the R1 times the amount of time. E to the R1 times the amount of time elapsing from small t to capital T. But because they are changing, I have to integrate them. So that's the trick. The trick is to break the U into buy and sell. So I break the U into U1 minus U2. U1 is the sell, U2 is the buy. Remember, if I sell 5 and buy 3, I'm net buying 2. U1 is bigger than 0, U2 is bigger than 0. But in order for me to change capital U into U1 plus U2, I need to have U1 times U2 equal to 0. That means I cannot have both positive at the same time. If this is 5 and this is 3, then that won't work, because if this is 5 and this is 3, then U is 2, but absolute value is 8. So that transformation doesn't work. So I need to say 5 times 3, which is 15, that doesn't allow. So this constraint rules that out. It says that only one of these guys can be positive. But that's nonlinear. I don't like it. I don't like a nonlinear constraint. But notice, nobody will be stupid enough to buy 5 and sell 3 and sell 5 and buy 3 at the same time. Because then the commission will be on the 8, $5 and $3, the commission will be on $8. So there's no reason to buy 5 and 3 at the same time. You might as well just buy 2 and pay the 2 commission on 2 and not on 8. So automatically, this condition will be satisfied. When you optimize, the stupidity will pay more, will cost you. And so rational individual will never do that. And so this will be automatically satisfied and we can ignore it. So once we ignore it, the problem becomes two control variables and both are positive or non-negative. And we can also show that this U1 has to be less than U1 and that U2 has to be less than U2. That's easy to see. And so this will be between 0 and U1 and this will be between 0 and U2. So now we have a problem where the control constraints are this. And we take the Hamiltonian here and we collect the terms in U only. So when we do that, we call it switching function W. And the switching function W, after we take only the control terms and reorganize it, it becomes this. So maximizing Hamiltonian with respect to U is the same as maximizing Hamiltonian with respect to U1 and U2. And the control U1 and U2 are bang bang. So here's the control U1 star, which is bang, 0, upper bound U1, depending on this quantity being negative or positive. Here's a U2 star, bang, 0 U2, depending on this quantity. You might take the minus on this side, so that this becomes minus 1 plus alpha lambda 1 plus lambda 2, depending on this quantity being negative or positive. So we have the form of optimal control. And it says what? It says, first one says, since U1 represents the rate of sale of securities, the first one says that the optimal policy is to sell at the maximum rate if the future value of the dollar less the broker's commission, that is future value of 1 minus alpha dollars. Because remember, if I sell $1, if I sell $1 of security, I only get 1 minus alpha dollar of cash. And when I sell the security, 1 minus alpha dollar of cash would be cash. And if the value of this cash, sale of securities, if the value of this cash is bigger than the $1 worth of securities, then I don't sell. Otherwise, I sell. So you can see what's going on. If this is, if I sell $1 of securities, I get 1 minus alpha dollar of cash. And 1 minus alpha dollar of cash by the marginal value lambda 1 for each dollar of cash, which we already told you is given by this formula. And because it's 1 minus alpha dollar, not $1, I have to multiply 1 minus alpha by lambda 1. So I multiply that. That is the value of that 1 minus alpha dollar, future value of that 1 minus alpha dollar. And the security that I sold, its future value is lambda 2. So if the future value of 1 minus alpha dollar cash is bigger than future value of $1 security, then our securities are not very good to keep. So I sell as much as possible. If I could sell infinity, I will sell all of them. But that's not, I'm not allowed here. If not the case, then I don't sell. The same argument applies to the second equation. If the suppose Suppose I want to sell, suppose I want to get $1 of security. If I get $1 of security, its value is lambda 2. But to get $1 of security, I must sell 1 plus alpha dollar of, I must use 1 plus alpha dollar of cash. And I lose that much value because that's the value of the 1 plus alpha dollar cash. So if the value I gain minus the value I lose is bigger than 0, then I buy as much security as possible. Otherwise, I don't do anything. It means 0. So these are very clear meaning now. And the bank solution basically has a very clear economic meaning. In the case the future value of dollar less the commission exactly equal to the future value of dollar this, then the optimal policy is undetermined, and we call it a singular control. That means if this is 0, then it doesn't matter what you do. But it's only at one instant, so it wouldn't make that much difference. Same thing, I already talked about that. This is the equation, meaning of the equation 5.17. So we already know what the meaning of these guys are. So if this is bigger than that, then this is clear. If this is bigger than that, this is certainly clear. So the control theory says if u1t is bigger than 0 because that's bigger than 0, then u2t is 0 because that's by second equation, the u2t has to be equal to 0. Similarly, this and this, so we know that this condition is automatically satisfied. We can prove it now. That's automatically satisfied. Of course, we can also eliminate it by economic argument that it will be foolhardy to buy and sell at the same time. Okay, so that's done. So the optimal policy is something like this. If I solve this problem, then I get the value of lambda at each point in time, which we already know is exactly given by is given by these guys. So lambda 1t, lambda 2t. So here's a picture. We also know that the terminal value of these guys 1, 1. Okay. So here's a picture. Given, what is given to us? Given to us is the interest rate R1t and R2t. They are given to us. The trajectory of interest rate is given to us. This is a deterministic problem. Don't ask me how we get it, but that's how we have it. So given that, we can compute lambda 1, lambda 2, and we can write these two equations. These are the equations which are the singular control equation where the two bank function switching functions are equal to 0. On this side, I buy securities, and this side I sell securities, and in between I do nothing. So when I solve the lambda 1 to lambda 2t, this is lambda 1, this is lambda 2, I will get the value lambda 1 0 and a lambda 2 0, which this point, right point, this point. And as I change over time, lambda 1 and lambda 2 will change, and we will have this path because eventually they will go to 1, 1. So this is the path of lambda 1, lambda 2. But this is not in terms of time, in terms of ratio of lambda 1 and lambda 2. This is the path of lambda 1, lambda 2. But we can rewrite this path in terms of time, and you can see that there is a singular control, and there is a buy securities, do nothing, buy securities, and this is what's going on here. And there's a sell securities right here. So we sell, do nothing, buy, do nothing, buy, and do nothing. So here it is. We sell, keep, do nothing, buy, again do nothing, buy, again do nothing. So this path is the same as this path in different space. So it's a very simple problem. It is a whole lot of economic intuition, which is very simple and very easy to follow. And remember, we solved the problem using control theory. We did not use here. We did not use a guess. We did not do anything. Even to show that this is coming free, we actually use optimal control theory or mathematics to show that that condition will be automatically satisfied. And then we solve for the entire problem and find a solution for any given R1t, R2t, any trajectory of two interest rates. Okay. So if you are interested, you you can compare this to Miller and Orr paper because they have a fixed cost and they have an EOQ model type model, and that has a different flavor of the policy, and we have a different flavor of the policy. Any question on this very, very simple model? And this was my second paper that I published, and this went into JFQA at the time. And this is, I don't know if it's the second or which one. This is another paper that also went to JFQA. So if there are no questions, I'm going to go to the second model. This is a much more interesting model than the first one. Once again, you can question all the assumptions because nothing is random here. But so we should use these models to learn control theory and to learn economic meanings behind things that are appearing all over the place. Those remain regardless whether the problem in the current setting. None of these papers, well, that one I don't know, but none of that papers would be interesting at this point in terms of their realistic features. I do want to tell you that one of my PhD students, Chutani, Anshuman Chutani, who's a professor in Nottingham in UK, he and Alain Ben Susan and I actually resolved this problem using R1t and R2t and dt to be stochastic. So we use stochastic processes, and the problem becomes more difficult. We use stochastic maximum principle, and we published that paper in Letters or something, and it extends this problem to stochastic situation. So that is a much more realistic problem, and it has been published and it has been done. This one, its stochastic version will be in chapter 12. So we know that this problem has been extended already a lot, but we are going to cover this in chapter 5 in high detail. So this problem was formulated by Krauss and Lee. Krauss was a professor at UCLA, Lee was a student, and then Lee became a professor at Santa Clara. I had visited Lee many years ago in Santa Clara. I never met Krauss myself, But anyway, this is their correction and extension of their paper. YT is the value of the firm's asset invested in capital at time t. XT is the current earnings rate in dollars per unit time t. So we have some assets and we earn some money. UT is the external or new equity financing expressed as a multiple of current earnings. This can be formulated a different way. You don't have to put it as a multiple, but whichever way we do it, we do it. So what is going on here? What we're going on here is that the company needs to finance itself. And it earns money from invested capital. It produces some goods and sells it or whatever. And when it earns money, it can pay dividends. And what it doesn't pay dividend, let me go one more step. Fraction of the current earnings retained, and 1 minus UT is the rate of dividend payout. So from its earnings, it can pay dividend. What is not paid as dividend, it invests. Retained earnings get invested. So that is the internal financing. I earn some money. Part of it is shown to dividend. That could be called consumption if you want, because I send it to people who are going to use this money to either invest or consume. But that's not this company's business. They have given the money, so it's been consumed as far as this company is concerned. And the other source of financing is new equity. It can sell stock in the market. Okay, it goes to an investment firm and say, this is the amount of new equity I want to issue. And the market will find out the price. And eventually at some price, if it's IPO, there's initial price offering, then the price can change in the market. And at that price, the people will buy the new equity. The money will come to the company minus the broker's commission, which is going to be given the next. And that money then comes to the company for investment. So company has two sources of financing, internal and external. And it pays out dividend. And when it does the external financing, it pays the cost. It's called the flotation cost or the transaction cost for external equity. So she's costed. That means that the way I do it is that I keep the same notation as Crofts and Lee so that it is people can compare it. But 1 minus C is the cost. So what you get is C times whatever. So if you sell $100 of stock, you get C times $100 money into your kitty for investing. Okay. Rho is the discount rate. R is the actual capital rate of return, actual rate of return on the capital. We assume it to be constant. And we assume that R is bigger than Rho because otherwise this firm doesn't have to be in business. Because I'm earning less than a discount rate, then there's no point earning, and there's no point doing anything. Because R is constant, I need to put some imposition on the upper bound of the growth rate. Because if R is bigger than Rho, and if I don't put any growth rate, then the optimal solution is to buy infinite amount of stock. Sell infinite amount of stock. Because I earn more than Rho, and people will be very happy to buy my stock, and so I can have infinite amount of it. And that's not what I want. If I don't put the growth rate, then I need to do something else, which has been done by me and Michael Toxer in a paper. Something else would be that the return on the capital decreases as I put more and more money in Y, which is reasonable because if you put more money on Y, more capital, and you have to look for sources of investment, you will find that you will put the money in the best possible investment and then the next possible investment. So as your capital grows, your opportunity to earn the same amount of earning will go down. Think about a company that drill for oil. So if it has $1 million, it will go to the best fertile ground where the oil is available. And if it has another $1 million, it will go to the next best ground. And so what happens is that the land or the area in which it will drill are becoming less and less productive. You do some study to see where the oil can be found, and based on that studies, you invest money into this. So that's a general theory that, so I need to somehow restrict R so that R doesn't stay bigger than rho for every Y. And that's another way to do it, and that's has been done, but not in this book. T is the planning horizon, and we'll talk about infinite horizon later. So current earnings, which is X, is nothing but R times Y. And the rate of change in the current earnings, which is X dot, because I need a state variable, the X dot is R times Y dot. But what is Y dot? Y dot is nothing but, remember, this is the amount I'm getting from selling external equity each per dollar. And this is the amount I'm getting from retained earnings. Okay, see retained earnings, 1 minus V is the dividend, the retained earning is what I retain, which is V. But these are expressed in terms of, you see that here, these UT are expressed as a multiple of current earnings. Multiple of current earnings. So you multiply, these are multiple of current earnings, so this is your current earnings, X. So X dot is R times Y dot, which is R times these times X. And I begin with X0. So that's my state variable. What is Y dot? Y dot is as an upper bound. It says I cannot, it says my upper bound G. So I need to write that in terms of mathematics. So the rate of growth is Y dot divided by Y. But I already know what a Y dot is, which is this CU plus V times X. And I already know what Y is. Y is X divided by R, which is this right there. So Y dot by Y given by this is given by this must be less than or equal to G. So that's a control constraint. I have two controls, U and V, and I have a constraint on the control which I must follow at each time T. So we have a state equation and we have a control constraint. And hey, Gautam, when you have a minute after the class, can you stick around? Oh, he's not there. Okay. The objective of the firm is to maximize its value. And this is interesting because this is where also these guys made mistakes, and I learned a lot from that mistake. And I wrote a whole lot of papers on that point afterwards, different than this paper. It's the present value of the future dividend stream accruing to the shareholder who are owner of the company at time 0. So notice, they're getting this dividend times X. This is the dividend they're getting. And it is discounted. And it's integrated. So that is the present value of the total dividend issued by the firm to these shareholders. So that must be the value of the firm. If you look at Miller-Modigliani theory, you will know that the share price, according to them, is the present value of the dividend that accrues to that share, and you discount it. Okay, this is even before Miller-Modigliani. Gordon had his own formula, Mike Gordon, and we'll say a little bit more about that later. So this is the value of the firm, and the firm is interested in maximizing that value. Let's say a little bit more about this, and yeah, so the maximize its value, which is taken to the present value of the future stream accruing to the share outstanding at time 0. So to derive this expression, note that this is the present value of all the dividends. Some of the dividends over time will also go to people who bought new equity, because they are new stockholders coming. So bought new equity. And they got dividend too, but not from time 0, but from the time they bought that stock. So I need to subtract the dividends that were issued to people who came afterwards, because at time 0, the company is only interested in maximizing its value to the stockholders at time 0. We will see that there is a very interesting aspect that's coming on here, and let's talk about that in a minute. So first, let's go one part. A portion of this dividend go to the new equity. And if you look at the efficient market, the new equity will exactly earn nothing but rho. So there are a lot of things going on here. There's a lot of finance going on here.
Excuse me, Professor.
Yeah.
Do you mind explaining y dot again? I was kind of lost. Why about y dot equal to cu plus v multiplied by x?
Okay, sure. So R is done, right? This R right here. So what is y dot? Well, y dot is the, so let's look at the y. Y is the value of the firm's asset invested capital at time t, right? This is my asset in investment, okay? Asset, capital, machinery, whatever. And y dot is the change in this capital, right?
Mm-hmm.
Well, where does the cat come from? It comes from new investment.
Mm-hmm.
The new investment is coming in two forms. One is the amount that I earn, and I retain part of the earnings. The rest I send as dividend. So V times X
Mm-hmm.
is the amount that I am going to reinvest.
Yes.
So that's your V times X. You see that?
Mm-hmm.
What about this? Well, I'm selling them a stock at time T as a multiple of current earnings, right?
Mm-hmm.
That's just, if you did not put the multiple, then this control variable can be defined to be another control variable. And in that case, it will now be multiplied by X.
Okay.
But that's just the way the guys formulated it. You could call it maybe W, and W2 is the stock, new equity in dollars, in which case this will become W, T times W, and X would not be part of this U, but only this. But it depends on whether you want absolute value or whether you want multiple of it. It's just the way the formulation was. I personally think that absolute value would be easier to follow than multiple, but this is what these guys did, and that's what I continue to do.
Mm-hmm.
So it's a multiple of whatever that is. Okay?
Mm-hmm.
So if this is 10, then multiple 5 times 10. If it's a multiple 5 times, then 5 times 10 is $50, right?
Mm-hmm.
And then C is all I get because 1 minus C goes to the broker.
Okay.
I get C. 1 minus C goes to the broker. I mean, normally people put C here and 1 minus C here, right? But then that would be the C going to the broker and 1 minus C coming to the company. But they did the opposite, just to make it, in order to not have 1 minus C here, they wanted it this way, so they have C here. Okay.
Okay, I got it. Thank you, Professor.
So, so this is understood. This is a little bit more complicated. This is the using an efficient market that says that in the efficient market, the new people cannot earn any more than rho. Because if they're earning more than rho, the price of the share will change so that they will earn only that much. So that means that the portion of the dividend that is accruing to these guys would have to be u times x e to the minus rho. U times x is the external equity. The discounted value of the external equity is this. So whatever they put in is equal to whatever they get. Because their return is exactly rho. So that's what they get. So I have to subtract this quantity from this quantity to get this quantity. So the net present value of the total future stock dividend that accrued to the initial shares is the difference of the previous two expressions, which is this. In explaining this formula, the previous paper, the original paper, also made a mistake, a huge mistake. And then their derivation was incorrect, and I tried to learn that, and that allowed me to learn a lot more about Miller-Modigliani theory. I wrote maybe several papers, including stochastic extension of Miller-Modigliani, and I've been thinking to write a book on it, which will be probably a 200-page book, but I haven't had the time. But the papers are available. The intuitive interpretation is simple. The intuitive interpretation is that the value J of the firm is the present value of the cash flows going out from the firm to the society minus the present value of the cash flows coming from the society into the firm. That makes sense, right? A firm is valued for the net outflow of cash from the firm to the society. So it is what it gives to the society minus what it takes from the society. This is what it gives to the society. This is what it takes from the society. So that is, now, if that's all they did, it would be fine. But what they tried to prove is using Miller-Modigliani, and that's where they made a mistake. And it can be done. And that's the subject of my MM papers, which I don't get into here because that's getting into finance, not optimal control. So as far as the optimal control is concerned, let us now agree that this is the objective function that we want to maximize. Remember, control theory would even, if you want to give this objective function, it will maximize this objective function, but it will not be a very interesting solution. But this is the objective function we want to maximize. Okay, so that's our problem. So we have now a problem. This is our problem. Oh, I forgot mine. So look at the problem and let me get my stuff on, which I put it somewhere else. Yeah. All these public recordings will have all of these other things, but that's okay. So I need the time. That's why I wrote myself up. Okay, so this is the problem that we are going to be concerned. Look at this. We have an objective function, which depends on u and x. V and u are the two control variables. We have one state equation with the initial value, and we have three control constraints. C plus C, u plus v less than z by r, u bigger than 0, and 0, v big, less than. So it is a nice problem. If it's a nice control problem, and its solution is not immediately obvious, although when we solve the problem, you will see that the solution is not that complicated. It is possible for somebody with a great deal of insight to actually solve this problem, uh, intuitively find the optimal solution for this problem. Okay. But then again, we are going to not only find it using the maximum principle, we explicitly solve it by using a technique called the reverse time construction. So let's begin. Hamiltonian is the objective function times lambda times the state equation. And the lambda dot is the derivative of that. And now you can see, Chusha, the derivative of lambda dot is going to depend on, it's going to change over time because there's a lambda on this side. But fortunately, there is no x on this side. So it is not a complicated two-point boundary value problem. But because of this, but it has a u and a v, so I mean, we still need to find those guys, and u and v may depend on other things. The transversality condition is lambda t equal to 0 because there's no salvage value here. And that also has some, so there are a lot of stuff that goes into this problem that I will tell you from time to time, whenever that happens. We will see that this salvage value, this says the company has no value at t. Whatever company is leaving at capital T has no value. And you will see that that particular condition having no value will complicate our case when we let t go to infinity. Because at t going to infinity, there is no value at the end. Generally speaking, there is no value. But because of that, we will see that having no salvage value could create some issues. And if the salvage value was there, we can still solve the problem. It's not a big deal. The problem there is, what is the salvage value? How do you find the salvage value? The salvage value of any state at time capital T is another optimal control problem that begins at T with whatever x you have, and again the same state equation. Right? That's all. I mean, what are you going to do with the company? Or you can liquidate the company, and it will be a liquidation value. But how do I know what the liquidation value is? Control theory can do whatever. It can find any function s of x and put it there and solve the problem. But in real life, somebody has to justify some s of x and how you get there. So right now, we go with Krauss and Lee. They have no salvage value. I have no salvage value, so I do like that. Hamiltonian is like this. You can write W1, W2, but these we'll call switching functions, where W1 is C lambda 1 and W2 is R lambda minus 1. The state variable x factors out so that the optimal controls are independent of the state variables. The optimal policy is kind of a bang-bang, but bang-bang in two variable is, as I mentioned to you at one time in chapter 3 or 4, I think it was, chapter 3, that when you have this, it's almost like a linear programming problem. So let's just look at that. This is a linear programming problem. Maximize W1U times W2U subject to this constraints. Because there are two variables, we cannot just go one extreme to another one. It is going to be one extreme point to another extreme point in a linear programming setup. Okay, that's simplex method problem. Notice now that W1 and W2 depends on these guys. And lambda is changing over time. And so this problem is to be solved at each point in time t. Notice there is a way, if you learn linear programming, you will also learn something called parametric linear programming. What does parametric linear programming mean? It means that you solve the problem at time 0, then you change the time from 0 and see whether the solution still stays the same. And you go as far as the solution stays the same, and then at some point the solution switches from one extreme point of the simplex to another extreme point of simplex. And then you will stay at that simplex point for a while until you go to the third point. So you go from one to the next as W1, W2 change over time. So you don't have to resolve the problem at every instant. You only have to resolve the problem at these switch points where the simplex method goes from one extreme point to another extreme point. We have two cases because the constraint is G by R, and we have two cases where G is less than R and G is bigger than R, and we will solve both of them. So let me tell you what I mean by that is, let me go not here, but let me go another place. And then soon we're going to finish. So here is first simplex. So this is the G by R less simplex. That's the first simplex. It says the following. It says that the W1 and W2 can have a different relationship with each other because this is the objective function. And depending on the objective function, the solution can be on, and this is the simplex, and these are the extreme points. This one, that one are extreme points. Well, you can also call every point here along these is also an extreme point. Okay, so they are all called extreme points. But notice, if W1, W2 is 0, the solution doesn't matter. It can be anywhere. But if W1 is less than 0 and W2 is less than 0, both are less than 0, you can sort of see that if they're both less than 0, then 0, 0 is a solution. And so what this guy says is, as W1 changes from this to this, the solution will go from here all the way to there. And then if W1 changes from there, the solution may go all the way from there to there, and so on. So we need to solve that problem over time. Why I have two cases? Because if I put G bigger than R, then you see that happens. The feasible space is no longer the whole triangle. The feasible space is this area. You can just draw this. Basically, this is drawing. This is the drawing of these three lines. That gives it the simplex. These three constraints define the simplex. So if you draw these three lines, you will see that these three lines are now become 4 lines, because you can see that I cannot allow this. So the simplex now has 1 point, 2 point, 3 point, 4 point here, and different W's will give you the different points which are optimal. So what I'm trying to now say is that linear programming problem of this kind can be solved graphically very simply by these two graphs. It tells you where I am with respect to W and tells me where the solution should be. It also tells me that if W1 is less than 0 and W2 equal to 0, then solution can be anywhere here. That's our singular control. It can be anywhere here. Then we want to see whether you can maintain that. So all of these are coming into play, and we can now summarize these two graphs into this table. This is very easy. Everybody who learned linear programming also learned how to solve it graphically. So we have these cases on W, and these cases will give rise to the cases that we will solve. So we'll call these cases A1, A2, A3, and these cases are B1, B2, B3, B4, B5. By the way, the book, third edition, doesn't work anymore because all of these have been relabeled this way. Initially, they were labeled not in sequence like this. They were labeled all over the place. And the optimal control for any of these conditions are given here. This is basically coming from, so you notice W2 less than 0, it's U star equal to V star equal to 0. Why I didn't put W1 less than 0? Because W2 less than 0 would imply W1 less than 0. So you don't need to put both of them. Okay. And you notice that I also put this control. So if it's W2 is 0, and W1 is less than 0, because W2 0, it will also imply W1 less than 0. So I don't have to put W1 less than W1 less than 0 doesn't have to be put here. It also says that U star is going to be 0, but V star can be anywhere between these two quantities. Of course, when G by R is, in the first case, this is going to be 1, because it's a min of these two guys. So it takes both pictures into account. So the cases, for example, one case says control can be anywhere from here to here. The other case says control can be anywhere from here to here. And so we have summarized all the cases that can happen at each point in time. Oh, we are actually out of time, right?
Yes.
Yes.
Okay. Yeah. So okay. Let me finish this. So we have all the preliminaries. We have solved the linear programming problem at each point in time. We now have to combine this. How do we put these things together over time? How do we synthesize all these cases from 0 to t? When they come in, when they go out, how do we organize all these? And that is going to be that we're going to do next week. That's going to be a reverse time construction technique using a technique where we change the time tau from t minus t as the new time and define everything and then solve this boundary value problem completely. Okay, so that's going to be the next. I want to give you the homework and then we are done. The homework is 5.2, 5.4, and 6.1. The last one was 4.13, 4.20, 5.12, right?
Yes.
Okay, so the homework due is 5.2, 5.4, 6.1. Due next week. I think we should be able to cover 5 next week and go to 6. We're catching up, even though we have 2 extra classes compared to the other people by having these sessions that were not allowed by the university, kind of, or were not allowed but canceled by the university. So thank you very much for coming.